Hi students, today we shall see the next point of memory management, that is demand paging. According to the concept of virtual memory, in order to execute some process, only a part of the process needs to be present in the main memory, which means that only a few pages will only be present in the main memory at any time. We have seen in the last lectures what is meant by virtual memory. With the concept of virtual memory, we can execute more processes than the capacity of the main memory. So, for virtual memory, we are going to use demand paging. However, deciding which pages need to be kept in the main memory and which need to be kept in the secondary memory is going to be difficult, because we cannot say in advance that a process will require a particular page at particular time. Therefore, to overcome this problem, there is a concept called demand paging is introduced. It suggests keeping all pages of the frames in the secondary memory until they are required. In other words, it says that do not load any page in the main memory until it is required. So whenever a process is executed, the whole process is never brought into the main memory, that is our RAM. Which pages are required, only those pages are loaded inside the memory. Whenever any page is referred for the first time in the main memory, then that page will be found in the secondary memory. The easiest way to implement virtual memory is through demand paging, where a page is loaded into the memory only when it is needed during program execution. That means when there is a demand for that particular page, then only that page will be brought into memory. Pages that are never accessed are never loaded into the memory. So pages which are never executed will be never brought into the RAM. A lazy swapper is used that loads only those pages that are needed. So the swapper which loads only the pages which are needed is known as a lazy swapper. The lazy swapper never loads all the pages of a particular process. The first issue with demand paging is how to recognize whether a page is present in the memory. So how the demand paging will understand whether the page is present in the main memory. The page table with valid invalid bit can be used for this purpose. An extra bit is added to the page table which will tell us whether the page is present on the memory or not. In demand paging, a valid bit means that the page is in the logical address space of the process and it is in memory at that time. Similarly, an invalid bit means that the page is either not valid or not in the memory. The page table entry for a valid bit is 1. So if the page is present in the memory, the valid bit will be 1 and will contain the frame address of the page. In case of an invalid bit, which means that page is not present in the memory, the page table entry will not contain any frame address. The second issue with demand paging is the situation when a process execution does not get a page in the memory. A situation will occur in demand paging when the page referenced is not present in the memory. This is known as page fault. This is a very important concept in demand paging. only because of page fault a page will be brought into the main memory. So page fault means what? The page which we are referring or the instruction which we are going to execute from a page, but that page is not there in the main memory. This concept is known as page fault. Whenever a process requests for a page, the virtual address is sent to the memory management unit. The memory management unit checks the valid bit in the page table entry of the page. If the valid bit is 1, it is accessed as in paging. Otherwise, the memory management unit raises an interrupt called the page fault or the missing page interrupt, and the control is passed to the page fault routine in the operating system. Processes reside on main memory. When we want to execute a process, we swap it into memory. When a page fault occurs, the operating system checks to see if any page frames in the memory are free. So now we are going to see how we are going to implement demand paging. So there are some steps which we are going to follow, which you can see in this particular diagram. So the procedure for handling this page fault is very simple. First is we check an internal table for this process. Every process will have a separate page table. So when the instruction is to be executed, we check the internal table of the process to determine whether the reference of the valid page, the particular page, is valid or invalid. So here in the diagram you can see when this instruction load M is to be executed, it will be first checked if that particular page is in the memory or not. If it is I, it means it is invalid, which means it is not there in the memory. If it is not I, means it is valid, it is in memory. So now in this diagram, in this given example, you can see that load M is on a page whose valid invalid bit is I. I means it is invalid. So if the reference was invalid, we have not yet brought that page. We now bring it later. So that this means this page is not there in the memory. We have to give a trap signal or an error message to the operating system telling that a page fault has occurred and we have to bring in the page. The operating system will that search that page in the backing store. It will find this page. Now this page has to be brought in the physical memory. For that it has to check if the physical memory has a free frame. So first step is reference, second an error message will be given, third we find a free frame. Then we are going to schedule a disk read operation and bring the desired page into the free frame. When the disk read is complete, we modify now this I has to be changed to V. That means the page is now brought into memory and it is a valid page. When the disk read is complete, we modify the internal table kept with the process and the page table to indicate that the page is now in memory. And then we restart the instruction that was interrupted by the illegal address trap. The process can now access the page as though it had always been in memory. After performing these steps, the CPU restarts from the instruction that it left off due to page fault. Okay, so these are the 6 steps which will be followed when the operating system finds a page fault. In an extreme case, the operating system could decide to start the execution of a process with no pages in the memory. As soon as the instruction pointer is set to the first instruction of the process, the memory management unit immediately raises a page fault interrupt. Now the missing page will be loaded into the memory. This technique is known as pure demand paging, which is based on the idea never bring a page until it is required. So this is all about demand paging. Next we shall see locality of reference. In some cases, programs access multiple pages from the memory with each instruction. This results in multiple page faults in an instruction. Locality of reference refers to a phenomenon in which a computer program tends to access same set of memory location for a particular time period. Locality of reference refers to the tendency of the computer program to access instruction whose addresses are near one another. Now this locality exhibits itself or is of two types. If a memory location has been referenced, there is a good chance it will be referenced again in a short period of time. This type of locality of reference is known as temporal locality, which deals with time. And next, second type of locality of reference is spatial locality reference. It means the fact that if a memory location is accessed, it is likely that the location near it will be accessed in the next instruction. This locality of reference is in condition with location. This is with time. So temporal locality refers to time and spatial locality refers to the place which the instruction will be executed. So this is all about locality of reference. This will be required in demand paging so that we can know that if one page is referred now, which will be the next page that will be referred. So depending on that, locality of reference is of two types. The last point for today is dirty page or dirty bit. A dirty bit can be added to each page table entry. The dirty bit is set by the memory management hardware when there is a write memory reference to that page, which means when we bring a page from the backing store into the RAM, that is we put it into a frame and there are some changes made to the page, that is there are some modifications made on the page, then we say that a particular page is a dirty page and the page table entry will be set on, that will be the dirty bit. When a page is first loaded into memory, the dirty bit is cleared, that is when the page is brought into memory for the first time, the dirty bit will be 0. If the dirty bit for the page selected for replacement is not set, the page has not been modified since it was loaded into the memory. So when we bring the page into the memory and if the dirty bit is not set, that is if it is not set to 1, it means that there are no changes made on this page. It is not a dirty page. Only replaced pages that have been modified need to be written back out to the swapping store. So when we bring a page into the memory and if there are no modifications made to that page, no need of writing that page back onto the backing store, because we are just copying the page from the backing store into the frame. If there are any changes to be made, then only we can write back or save the changes to the backing store. So this dirty page or dirty bit helps to reduce the overhead of writing each and every page back to the hard disk. So in this case we can only write back to the hard disk the pages which are modified. Thank you.